So in the previous class, we have seen that an atomic gas laser usually has very poor quantum efficiency. Today, let me spend some more time to elaborate this point further. See, we also have seen in the last class that the inverse square dependence of energy with the orbital quantum number essentially manifests as the electronic energy level getting increasingly closer to each other with increasing excitation. As the excitation increases, the energy level comes closer and closer. So it is n equal to 4 and n equal to 5 will be even closer to n equal to 4 and n equal to 6 will be even so on. So how does this reflect as far as quantum efficiency of a gas laser is concerned, this fact? Let us assume that we will make a laser using these three levels, the energy level on which the operation of the laser is based. This is just to clarify, to make this point easily understandable to you, that why quantum efficiency of gas laser is very best. So this is our ground state. So to begin with, all the atoms reside in this. And suppose this is our upper level and this is our lower level. So basically we'll have to transfer atom from here to the upper level, and the lasing will occur between these two. So the light will be emitted from this direction, laser light. So if you have to check a lone atom, but now you see, because this level is empty, therefore even if you take a lone atom from here to here, you will create population inversion, there will be lasing, fine, absolutely fine. But to take just one atom from here to here, you have to spend an energy which is E3 and this is E1. E3 minus E1. This much energy is being expended to take an atom from the ground state to the upper level. And of this energy, a small fraction is emitted as photon. So of this energy, E3 minus E2, this much energy is being emitted as a photon. And rest of the energy, that is E2 minus E1, stays back into the system without any contribution to the emission. Now, quantum efficiency is defined as the fraction of the excitation energy that is emitted as photon. So you see, the excitation energy is this much, and of which this much energy is emitted as photon. So the quantum efficiency is defined as the fraction of the excitation energy that is emitted as photon. So it will be E3 minus E2 by E3 minus E2. Now you can see in this particular case, E3 minus E1 is much more compared to E3 minus E2. And basically E3 minus E2 is much less than E3 minus E2 is much less than E2 minus E1 or E3 minus E1, and hence this will be much less than much less than 1. So that is why quantum efficiency of the laser, namely 3 minus C2 by 2, is intrinsically small. This is because lasing occurs far above the ground state. This is the ground state, lasing occurs here. So this much energy stays back into the system and is often dissipated as heat. This is why atomic gas lasers usually emit in the visible and near infrared region, and they will hardly able light, will emit light at ultraviolet. That is, high frequency light cannot be attained from the operation of an atomic gas laser. I hope I have made it clear to you as to why a gas laser normally has poor quantum efficiency. Now, if it has poor quantum efficiency, then what kind of efficiency can gas laser eventually give? Well, let us try to find it out. What will be the actual operating efficiency of a gas laser? The operating efficiency is will be much lower than quantum efficiency. Why? Because you see, the pump energy is first realized as the kinetic energy of the electron in the discharge. You know that. The energy that you draw from the line, that is the pump energy. What in a discharge, what happens? Suppose if you have this gaseous medium. I'm considering a very simple case. You have put your gas here and you are trying to create a discharge. So you have connected this supply line and you apply a voltage here. So the electron actually will experience force and thus would be accelerated towards the if we consider the case of electron, they'll be accelerated towards the positive electrode, and as they're accelerated, they'll gain velocity and thus acquire kinetic energy, and after acquiring sufficiently high kinetic energy, they can collide with other atoms or molecule, other atoms present in the gas in this system, and such collisions, electron will collide with a neutral atom and it has acquired kinetic energy, and then this collision, actually if the electron has enough kinetic energy, it can actually ionize the atom and create an additional electron, and this electron will then move with reduced kinetic because some of the kinetic energy of the electron has been used up in ionizing the electron. So this way electrons will be created, and as the more and more electron will be created, they will again be accelerated, and this process will continue. Thus, you eventually create an avalanche of electrons, and this basically sustains the discharge. Therefore, the pump energy, that is the energy that electrical energy that you draw from the line, is first transferred as kinetic energy of the electron, and then part of the kinetic energy will be transferred as internal energy of the atom, because in some of the collision the atom will be excited to its excited state where you want that atom to be excited, and of course electron will move with less kinetic energy. So then the pump energy is first transferred as kinetic energy of these electrons which are in the discharge. Of course, there will be positive charges, that is ions also, but ions do not contribute so much to the flow of current because their mass is very high, so they would not acquire much higher kinetic energy. All right. So then let us come back to this. So the pump energy is first realized as the kinetic energy of the electrons in the discharge. So electrons will have varying kinetic energy in the discharge, and velocity, therefore they will have widely varying velocity. The velocity distribution of the electron is actually Maxwellian in nature. I think you have all read this when you studied kinetic theory of gases. Only a fraction of these electrons can only populate the upper laser level efficiently through collisions. You see, the electrons' energy, kinetic energy, it will have wide-ranging kinetic energies. Different electrons will have different kinetic energy, and then they will have the velocity distribution will follow a Maxwellian distribution. So electrons will have number of electrons with velocity. There will be electrons with low velocity, moderate velocity, and also very large velocity. Now, all these electrons are not equally effective in transferring molecules, atoms from the ground state to the energy level of our requirement. Only a certain group of only electrons belonging to, say, certain velocity group will be most efficient to transfer atoms from the ground state to the upper laser level. So we want that the atoms will be transferred from the ground state to this state, which is the upper laser. Therefore, only a fraction of the pump energy, because pump energy has been distributed, is now distributed with as the kinetic energy of all these electrons. Only a small fraction of that will be utilized to create population inversion. So then the efficiency of pumping will be extremely small. Now, quantum efficiency is already small. Therefore, the pumping efficiency will be, therefore the overall efficiency of the laser is going to be much smaller. I think you have understood this, that why the operating efficiency of a gas laser will be even lower than quantum efficiency. For example, say if the laser, if the entire pumping energy can be consumed to transfer the population from the ground state to excited state, the entire pumping energy, if it can be utilized, so all this energy, if it can be utilized to pump the atom from the ground state to excited state, then the operating efficiency of the laser will be just equal to the quantum efficiency. But that is impossible. You cannot utilize all the energy that is being stored as kinetic energy of the electron to excite the atoms from the ground to the excited state. Therefore, the actual efficiency, operating efficiency of the laser will be equal to quantum efficiency into the pumping efficiency. Suppose, let us assume that for a particular gas laser, the quantum efficiency is, say, 1%. And suppose the pumping efficiency, that is, if you have used 10 joule of energy, drawn 10 joule of energy as the pump energy, and 10%, if 10% pumping efficiency is 10%, that means only 1 joule of pump energy is being utilized to transfer atoms from the ground state to the upper laser level to create population inversion. So the efficiency, operating efficiency of the laser will be 1% into 10%. So that will be equal to 0.1%. I hope you have understood that why the operating efficiency will be even lower than quantum efficiency. the working efficiency actually of an atomic gas laser can typically lie within 0.01% to 1.1%. So atomic gas lasers do not give very high operating because of this reason. I hope you have understood this point well. All right, now let us turn our attention to the helium operation of helium neon, which is one of the most important atomic gas. Now, helium neon laser has the distinction of not only the first gas laser, but also the very first continuously working laser. You know, the first laser that Mayman operated, it was a pulse laser, pulse solid state laser, of course. And helium neon laser was not only the first gas laser that was operated, of course, soon after the operation of the first ever laser, but also it was the first continuously working. It was invented in December 1960 by Iranian American scientist Ali Jahan and his co-workers at the Bell Laboratories located in Murray Hill, United States of America. It is one of the most common and popular gas lasers. Laser operates by striking an electric discharge in a low pressure gaseous mixture comprising 5 parts of helium and 1 part of neon. Neon plays the role of light emitting species, while helium helps to create and maintain population inversion. So, helium is not the light emitting species, but it helps creating population inversion in neon, which is actually the light emitting species. Therefore, helium basically performs the low role of surrogate gas here. So let us try to understand a little more detail, about the role of helium. A general explanation where pumping occurs through impact with electrons in a discharge, assuming the light emitting species has more closely spaced energy levels, close to levels between which lasing transition takes place. This is where a surrogate gas is important, use of surrogate gas. Let us try to elaborate. You see, let us assume a gas which is atom, which is your light emitting atom. Suppose this is it, we call it A, atom A, the atom of kind A. This is its ground state. And suppose this is the upper level, and suppose this is the lower level, and it so happened that there are many more energy levels are also located between lower level and the ground state. And when you create a discharge in this gas, then these atoms in the ground state will, in the discharge, will collide with electron, and this collision can bring this atom in any of these states, of course depending on the energy of the electron, and not only selectively bring the atom to the upper laser level where you want them to come for creating population inversion, depending, because these electrons are distributed. This is the velocity distribution. So there will be collisions, all kinds of collisions, bringing this atom to different energy levels. So creating population inversion between this and this two states will be nearly impossible. This level also will be populated, and many collisions will just unnecessarily waste the energy of the electron, bringing them to so many other levels. Or of course, some will of course bring it to the upper level, but creating population inversion would be next to impossible. Impossible. So how do you get around the problem? You use a second basis, which you call B. And you choose this in such a way that you have this as a energy level which is very close to the upper laser level. And there is no other energy level located in between this and this. So I think you have now understood the advantage that this will give you if you add this and put both this in the discharge. And now electron in the discharge will collide with both B and A. So if the electron collides with B, then because there is no other level between these two, most of the collisions of B that the electron will have with B will bring it to this state, which is this state, less carried. Of course, there will be some energy levels which is above it. They would also be populated, but not to a very great extent. While this will continue to have its own kind of collisions and transfer of population from the ground to the different states. But net effect will be, you will create a number of B atoms in this state, this excited state. So next what will happen? This B atom in the excited state will collide with neon atom at the ground state. Sorry, this A atom at the ground state. And because these are very closely spaced, so the excitation energy of B will simply be transferred to excitation energy of A and bring it up here. So basically what will happen? This will transfer its excitation energy to A. So A will be excited and B will come down to the ground state. And as this process will continue, so excitation energy of B then will, lot of excitation energy from B will then be transferred to A, and in effect will create a population inversion between this level and this level, because the collision between B and A will not bring A to any of these levels, because only this much energy is involved which can bring A to this level and not to any of these levels. So this way you will be able to create population inversion. And if you can add B, make B's number appropriately large compared to A, then most of the collisions, more number of collisions the electron will have with B, number of collisions the electrons will have with B will be more than A, because B is now more than A. So such atom, this atom here plays the role of surrogate. So with this, now let us get back to the working of helium. So these are the energy levels of both helium and neon that participate in the lasing process. These are the energy levels of neon, and these are some of the low-lying energy levels of helium. There will be other levels which are above this, which we are not considering. They don't participate in the lasing process. These are the few low-lying energy levels which participate in the process of lasing, which you have considered here. Now the second orbit, that is N equal to 2, of the electrons in the helium atom is split into two long-lived metastable sublevels, 2,1s0 and 2,3s1. Let me very briefly explain the splitting of this. You see, the electron rotating in an orbit intrinsically possesses an angular momentum. And it also spins about itself, similar to Earth's rotation about the sun and itself, which gives or creates our day and night. So electron also has spin angular momentum. Because it rotates, it has an intrinsically positive angular momentum, and because it spins about itself, it also has a spin angular. And as the electron's energy is quantized, its angular momentum, both orbital as well as spin, are also quantized. These effects cause the energy levels of the electron in the various excited states to split into sublevels, denoted by the orbital quantum number n, angular quantum number, orbital quantum number L, and spin S. However, these are all spectroscopic features and outside the scope of this course, and I will not deal them in much great detail, but only remember that because of this, the energy levels are also split into many sub-levels, and often these sub-levels are metastable. That means they do not very quickly relax to other levels. Now, so let us move forward then. So these are the energy levels. Now, inelastic collisions that the helium atoms in the electronic ground state undergo with the electrons present in the discharge result in their excitation to both these. As the helium collides with electrons in the discharged ground state helium, both these levels will be excited. Electron will transfer its kinetic energy and take helium to both these levels. Both are metastable through this reaction. Helium in the ground state collides with electron, which has now appropriate kinetic energy, and these collisions brings helium to this state. An electron now will move with less kinetic energy because some of the kinetic energy has been given in order to bring the helium from its ground state to this state, ground state to this state. And then also some collisions of helium, ground state electron will also bring it to this level. These levels have a very close match energy with the 5s and 4s levels of neon. 5s and 4s levels of neon. These are the upper level for the neon. And as the excited helium atom collide with ground state neon atoms, near resonant exchange of energy takes place between 2s0 and 5s as well as 2s1 and 4s. Just like as I said, helium here works as the surrogate atom. So helium, when collides with the neon ground state atom, the neon ground state will be transferred to the upper laser level and helium will come down to the ground state. Similarly, the helium from its this state, when collides with neon ground state, neon will be excited to its upper level. There are two upper level levels here, and helium will go down to the ground state. And little mismatch of this energy, it may not be exactly same, slight mismatch, that will be compensated by the thermal energy, which is always present, omnipresent, except when the gas is at 0 degree Kelvin. Such collisions are extremely fast and probable because they are almost resonant. So then we have come to this point. By taking advantage of helium, we have actually populated the upper levels of helium. I think I'll stop here today, and tomorrow we'll begin from this point that we have attained population inversion, and we'll move further in the operation of helium. Let me stop here today.